So for today's lesson, we will discuss crustal deformation. Crustal deformation. The tectonic movement of plates results in the crustal deformation. For example, folding and faulting of our Earth crust. Recall the different types of stress. So you may recall as confined stress, tensional stress, shear stress, and compression stress. Those are stresses acting upon or can influence a rock's behavior. So in this case, we are talking about tension. So these tensions in rocks can also play an active role in the movement of plates. So this explains that crustal deformation refers to the changing Earth's surface caused by tectonic forces that are accumulated in the crust and then can cause earthquakes or earth tremor or earth movements. The slow background tectonic motion between the Earth's plates, thereby constraining the buildup of stress on fault lines that result in different types of deformation. So we have the first type of crustal deformations, the folding. Geologic folding is a type of earth movement resulting from the compression of rock strata or rock layers. Bending, curving, crumbling, or buckling of rocks into folds is usually visible on a strata. Folding results from compressional forces because of high temperature and pressure from interior of the Earth. An example of landform created as a result of folding is the Himalayan mountains. So the Himalayas or the Himalayan mountains are a prime example of how tectonic plate motion can manipulate the Earth in extraordinary ways. So these Himalayan mountains was formed in compressional forces. So these colliding plates resulted in the formation of the highest mountain range on the planet, the Himalayas mountain ranges. So our continents are carried by a series of tectonic plates located in our Earth's lithosphere. So another example is like a sheet of a plywood, a tectonic plate is more resistant to pressure when bent against the grain. So in other words, large damaging bending earthquakes are most likely to occur where the subducted plate's own gesture aligns with the direction of its downward bend. So as you can see in our above image. That's why bending or curving or crumpling or buckling of rocks will turn into different types of faults. It's usually visible in the layers of rocks or the rock strata. Causes of geologic faults. The faults arise as a result of tectonic pressure and stress in the rocks, and rather than fracture, they may fault. They are easily visualized by the loss of horizontality of strata. When tectonic forces acting on sedimentary rocks are a number of characteristic forms, the geologic faults also helps us to make geologic maps, which we use to infer underground structures where we can't see the rocks and to help us to understand the formation of geologic resources to locate and manage them. So in addition to this, geologic maps are uniquely suited to solving problems involving Earth's resources, hazards, and environmental issues. Geologic maps represents also this distribution of different types of rocks and superficial deposits, as well as the location of geologic structures such as fault lines and faults. Okay, so let us now proceed to the parts of a fold. Upthrown part of a fold is called anticline, as you can see in our image. Downthrown part of a fold is a syncline. The side of the fold is a limb, and the top of the fold is the crest. The plane which bisects the angle between two limbs is called the axis of fold or axial plane. Based on our image, the fold is formed by the plate movements. So we have the first type of fold, the symmetrical fold. When compressional forces is equal from both sides, symmetrical fold could happen. The angle of the limb is same on both sides, such as a fold is called a symmetrical fold. So this first type of fold, the symmetrical fold, are folds whose limbs have approximately the same angle of dip relative to the axial surface, also known as a normal fold. Next, we have asymmetrical fold. When compressional force is more from one end, one limb is stiffer than the other. Such a fold is called asymmetrical fold. So in addition to this, a symmetrical fold forms when a fold whose limbs are unequal in length, as you can see in our image, and the axial plane is inclined, dipping in the same direction as that of the gently dipping limb. Next, we have the isoclinal folds. Isoclinal folds are similar to symmetrical folds, but these folds both have the same angle and are parallel to each other. So iso means the same and symmetrical, and cline means angle. So this name literally means the same in angle. That's why it is parallel with one another. So in addition to this, isoclinal folds may have a similar angle and composition. Next, we have the overturned fold. When one limb of the fold is pushed, as you can see in our image, it's pushed over, the other limb of the fold is called as overturned. Limbs are seldom horizontal because of the push. So in addition to this, an overturned fold are also called overfold. It has the axial plane inclined to such an extent that the strata or the layer of the rock on one limb are overturned rapidly. Next, we have the recumbent fold. So when one side of the fold is pushed so much that it lies positioned over the other, such a fold is called a recumbent fold. So in addition to this, a recumbent fold results from flow that maintains the general coherence of the layering with overturn due to frictional drag. The general horizontal configuration of the axial plane reflects equilibrium of the rocks in the Earth's gravitational field. So let us now proceed to fold mountains. When plates converge, the weak rocks and sediments lying between two plates get squeezed and folded. Parallel folds form long chains of fold mountain ranges with high peaks. The fold mountains are characterized by peaks and valleys. The top of anticlines become the peaks and synclines become the valleys. Intermontane plateaus or plateaus surrounded by mountain ranges in all sides may be found between the high ranges, for example, the Tibet Fault Mountains. So in addition to this, if fault mountains are created where two or more of Earth's tectonic plates are pushed together, all these colliding here in the Philippines. So these fault lines or geologic faults are called the West Segment, also known as the West Valley Fault. It is one of the two major fault segments of the Valley Fault System, which runs through Metro Manila to the cities of Marikina, Quezon City, Pasig, Makati, Taguig, and Muntinlupa, and moves in the dominantly dextral strike-slip motion. So the fault involves in this kind of fault lines or geologic fault is a strike-slip motion or strike-slip fault that could result to a big earthquake or the big one. So we have the parts of a fault. Fault consists of two rock blocks that displace each other during an earthquake or regular tectonic movement. One block is called the hanging wall. So mas mataas yung hanging wall kaysa sa footwall. And the other is the footwall, nasa baba. Understanding the parts of a fault can help you identify what type of fault you are seeing. So we have the parts of a fault in summary. So we have the first one, the fault plane. We will base our description in our image representation. So fault plane defines the surface area between two rocks blocks created by an earthquake. Okay, so there is the movement or the opposite movement of forces. That is the other one is going upward and the other one is going downward. So the fault plane is in between that two moving plates. So we have the fault trace, the visible crack in the Earth's crust that indicates where a fault is, as you can see in our image. We have also the fault scarp, the vertical step that rises during tectonic activity. So if the hanging wall will move upward, it will create fault scarp. Next, we have the hanging wall, the rock block that hangs over the fault plane. And also we have the footwall, the rock block that occurs below the fault plane, as you can see in our image. Okay, so we have the significance of faults. Faults are an important part of geology, as they form along planes of weakness in the rocks. This allows geologists to study the stresses involved in the formation of these faults, and thus infer the processes that form the fault. Faults are fractures in a rock with movement along them due to tectonic pressures. Movement along these faults is the cause of most earthquakes. There are two types of faults: strike slip and deep slip. So in addition to this, the faulting patterns created by faults can have enormous economic importance. Faults can control the movement of groundwater, and they can exert a strong influence on the distribution of mineralization and subsurface accumulation of hydrocarbons. They can have a major influence on the shaping of the landscape, as you can see that a fault can create earthquakes, and earthquakes can shape the earths. Next, we have the types of fault. First one, we have the normal fault. So normal faults occur when the crust of Earth is extended, causing two rock walls to move farther apart from one another to accommodate for extension. So in terms of how we describe a normal fault, the footwall is higher than the hanging wall. That is a normal slip or a normal fault. Next, we have the reverse fault or thrust fault. Reverse faults occur when the crust of the Earth is compressed, causing the two rock walls to move closer together. Because of the compression, the hanging wall is above the footwall, as you can see in our image, and it accommodates for the pressure because it applies compressional stress. It's also called the reverse slip. Next, we have the strike slip fault. This is where the fault plane within the rock is near vertical at around 90 degrees from the horizontal surface. There are two types of this fault: the left lateral and right lateral strike slip fault. So we have the first one, the left lateral strike slip fault. So when you stand on one side of the fault and look towards the other side has appeared to move to the left side. Okay, so that is why it is called a left lateral strike slip fault. Next, we have the right lateral strike slip faults. So when you stand on one side of the fault and look towards the other, so the other fault may move to the right or appeared to move to the right. That's why it is called a right lateral strike slip fault. So we will now discuss seafloor spreading. The concept of seafloor spreading was developed by geologist Harold Heast in year 1895 to 1982 and Robert Deitz in year 1914 to 1995. They coined the term seafloor spreading and showed how it aligned with the unexpected ideas of the continental drift. So in addition to this, the seafloor spreading creates a successively younger ocean floor, and the flow of material is thought to bring about the migration or drifting apart of the continents. So basically it is supporting the continental drift theory. Seafloor spreading is a continuous process where tensional forces on both sides of the plates cause them to constantly move apart. Magma rises to the surface from the mantle, as you can see in our image. So in time, the magma is cooled by seawater. So when it's cooled, it forms the oceanic crust. New rocks then form in this area. Since the newer rocks are younger in geologic features, scientists are able to determine areas of seafloor spreading because of the types and composition of new rocks in those areas. Rocks from the separated plates would have similar rock types and composition, usually as sedimentary rocks or sedimentary type, because of all the exogenous processes that these rocks were subjected to, while the area at the center would have mostly igneous in type. Hence, the center of seafloor spreading happens along mid-ocean ridge. This is exhibit an actual site of seafloor spreading occurring at the mid-Atlantic ridge. So seafloor spreading helps explain continental drift theory of plate tectonics. When oceanic plates diverge, or tensional stress causes the fractures to occur in the lithosphere. The plates that are not subducting are driven by gravity, sliding off the elevated mid-ocean ridges, called the ridge push. Ridge push or sliding plate forces is proposed driving force for plate motion in plate tectonics that occurs at mid-ocean ridges, as you can see in our image. So let us now proceed to trenches. As we can see in our image, oceanic trenches are topographical depression of the seafloor, relatively narrow in width but very long in length. So these oceanic features are the deepest parts of our ocean floor. Ocean trenches or oceanic trenches. Ocean trenches are long, narrow depressions on the seafloor. These chasms are the deepest parts of the oceans, and some of the deepest natural spots on Earth. Ocean trenches are found in every basin on the planet, although the deepest ocean trenches the ring or the Pacific Ring as part of the so-called Ring of Fire that also includes active volcanoes and earthquake zones. So this explains that trenches are so deep because they are formed by subduction. A subduction is a geophysical process in which two or more of Earth's tectonic plates converge, meaning the stress applied is in compression. Denser plate is pushed beneath the lighter plate and the deep into the mantle, causing the seafloor and outermost crust, the lithosphere, to bend and form a steep V-shaped depression. And as the V-shaped depressions are formed, it creates ocean trenches. So the ring of fire in our below image are also referred to as a circum-Pacific belt. So circum-Pacific belt is a path along the Pacific Ocean characterized by active volcanoes and frequent earthquakes. The abundance of volcanoes and earthquakes along the ring of fire is caused by the amount of movement of tectonic plates in the area. So in the ring of fire, so we have these several types or different structures of trenches, as you can see in our image. So over millions of years, the rising magma creates a series of active volcanoes known as volcanic arc. If you were to drain the water out of the Pacific Ocean, you would see a series of deep ocean trenches that run parallel to corresponding volcanic arc along the ring of fire, as you can see in our image. Ocean trenches are a result of tectonic activity, which describes the movement of the Earth's lithosphere. In particular, ocean trenches are a feature of convergent plate boundaries, where two or more tectonic plates met. At many convergent plate boundaries, a dense lithosphere melts or slides beneath less dense lithosphere in a process called subduction, creating a trench. Ocean trenches occupy the deepest layer of the ocean, the hadal pelagic zone. So the hadal pelagic zone or the hadal zone is the deepest region of ocean lying within oceanic trenches. The hadal pelagic zone is found from a deep around 6,000 to 11,000 meters and exists in long but narrow topographic V-shaped depressions. So it is believed that most life at this depth is sustained by marine snow or the chemical reactions around the thermal vents. The low nutrient level, extreme pressure, and lack of sunlight create hostile living conditions which few species are able to exist. So as no sunlight reaches this layer of the hadal pelagic zone, the deep sea creatures have reduced eyesight. So with very large eyes, as you can see in our image, for receiving only bioluminescent flashes. So most of the bottom dwelling creatures lack pigmentation because coloration is not useful in the environment with no sunlight or with no light at all. So the intense pressure, lack of sunlight, and frigid temperatures of the hadal pelagic zone make ocean trenches some of the most unique habitats on the planet Earth. So how trenches form? The reason behind is the subduction zones. So when the leading edge of a dense tectonic plates met the leading edge of a less dense plate, a denser plate bends downward. In this kind of situation, we are referring to a convergent plate movements, wherein compressional stresses occurs. So this place where the denser plate subducts, so is called a subduction zone. If those plates subducts or move to one another, wherein one plate is under the other plate. Oceanic subduction zones almost always feature a small hill preceding the ocean trenches itself. This hill, called the outer trench swell, marks the region where the subducting plate begins to buckle and fall beneath the more buoyant plate. So plates are denser in the subduction zone because oceanic plates are made of basalt rocks, so they are denser. The oceanic plate is denser and sinks due to its lower buoyancy. It is sucked in the asthenosphere and is melted deeper into the earth, called a subduction zone. So some ocean trenches are formed by subduction between a plate carrying continental crust and a plate carrying oceanic crust. Continental crust is always much more buoyant than the oceanic crust, and oceanic crust will always subduct. So oceanic crust is the plate under the subduction zone. Oceanic trenches formed by this continental oceanic boundary are asymmetrical on a trench outer slope. So the slope is gentle as the plate gradually bends into the trench on the inner slope. The trench walls are much more stepped. The types of rocks found in these ocean trenches are also asymmetrical. The oceanic side is dominated by thick sedimentary rocks, while the continental side generally has a more igneous and metamorphic composition because of it is located in the magma chamber. Some of the most familiar ocean trenches are the result of this type of convergent plate boundary. For example, the Child or the Child Trench off the west coast of South America. This formed by the oceanic crust of the Nazca Plate subducting beneath the continental crust of the South American Plate. The Ryukyu Trench, stretching out from southern Japan, is formed as the oceanic crust of the Philippine Plate subducts beneath the continental crust of the Eurasian Plate. So according to National Geographic, the Child Trench off the west coast of South America is formed by the oceanic crust of the Nazca Plate subducting beneath the continental crust of South American Plate in a subduction zone. Some of the molten material, the former seafloor, can rise through volcanoes located near this trench. On the other hand, the Ryukyu Trench is the result of oceanic crust of the Philippine Plate obliquely subducting beneath the continental crust of the Eurasian Plate at a rate of approximately 52 millimeters per year, in conjunction with the adjacent Nankai Trough to the northeast. Subduction of the Philippine Plate has produced 34 volcanoes. So more rarely, ocean trenches can be formed when two plates carrying oceanic crust met. The Mariana Trench in the South Pacific Ocean is formed as the mighty Pacific Plate subducts beneath the smaller, less dense Philippine Plate. So in our figure, it represents the Pacific Plate subduct with the Philippine Sea Plate. So why is the Pacific Plate subducting beneath the Philippine Plate? So the reason is ultimately it was a change in the movement to a westward motion of Pacific Plate that converted the north-south transform fault on the Philippine Sea Plate to the subduction zone, currently present along the boundary between these two plates. So let us now proceed to mountain formation, the types of mountains, and also the examples related to mountains. Mountain formation. What are mountains and how are they formed? A mountain is a geological landform that rises above the surrounding land. Mountains result from the collision and friction between tectonic plates in the Earth's crust, or between subplates components of the plates. Tectonic plates move very slowly, can take millions and billions of years for mountains to form. The Himalayan mountains began forming this way about 55 million years ago. The Himalayan mountain ranges has 30 of the world's tallest mountains. As you can see in our image, including Mount Everest, which soars 29,035 feet in the air, and it is the tallest mountains in the world. So mountains are formed by slow but gigantic movements of the earth crust. So the outer layer of the earth. So the earth crust is made up of huge slabs called plates, which fit together like a jigsaw puzzle. When two slabs of the earth crust smash into each other, the land can be pushed upwards, forming mountains. So the Himalayan mountain range and the Tibetan plateau have formed as a result of the collision between the Indian plate and Eurasian plate, which began 50 million years ago and continues today. 225 million years ago, India was a large island situated off the Australian coast and separated from Asia by the Tethys Ocean. So that is how we call our um, continental drift theory, wherein we have the Tethys Ocean. The ocean belongs to the supergiant continent Pangaea. Mountain formation, according to the tectonic theory, is represented sometimes by two arrows opposite to each other, and a single mountain block in between. We mean that the arrows are plates push the mountain block up, and based on this idea, it is thought that mountains are a collection of rocks put together on top of the continental crust, and they are completely isolated from Earth's mantle that is made of a basalt rock. So commonly, movements of tectonic plates creates volcanoes along the plate boundaries, which erupt and form mountains. The volcanic arc system is a series of volcanoes that form near a subduction zone where the crust of sinking oceanic plate melts and drags water down the subducting crust, wherein we can therefore conclude that the Earth's mantle is made of basalt rock and it is completely isolated with the formation of these mountains. The Earth is not the only planet that has mountains. All the rocky planets have mountains too. There is no water on the moon and it does not have a continental crust as the Earth does, but it has mountains that are exactly the same as mountain on Earth. See the picture, as you can see, we have mountain formations that has already found on the moon. There on the moon, the mountains are connected directly to the basalt layer that is equivalent to the seafloor on Earth. And this shows that mountains are not pushed by the continental crust because there is no continental crust on the moon. In other words, mountain rocks were dropped from the sky in trenches and then pushed up by a rising magma from could not have happened before the addition of rocks that created mountains and lowlands 200 million years ago. So the Ring of Fire is important because it's the home of 75% of the world's volcanoes and 90% of its earthquakes. About 1,500 active volcanoes can be found around the world. So this movement results in deep ocean trenches, volcanic eruption, and earthquakes epicenters along the boundaries, where the plates map called a fault lines. So let us now proceed to the types of mountains. So the first one, we have the fault block mountains. Rocks in the Earth's crust can create massive blocks of rock that then move apart. As they move, one block may slide under another, pushing it up. This leaves large blocks of rock sticking up high above the Earth's surface. These are fault block mountains. Example of this, we have the fault block mountains in the Sierra Nevada mountains in North America. So fault block mountains were formed as blocks of rock moved up or dragged along faults. These are formed also by the movement of large crustal blocks when two forces in the Earth's crust pull it apart. Some parts of the Earth are pushed upward and others collapse down. Next, we have the Dome Mountains. So when large amounts of magma under the Earth's crust bubble up towards the surface, the layers of rock above the magma are pushed up to form dome mountains. The inside of these mountains is filled with magma that has cooled and hardened. As the dome is higher than its surroundings, erosion by wind and rain occurs from the top. This results in a circular mountain range. Domes that have been worn away in places form many separate peaks called the Dome Mountains. So in addition to this, dome mountains are formed from hot molten material, that is magma, rising from Earth's mantle. As you can see in our image, into the crust that pushes overlying sedimentary rock layers upward to form a dome shape. So unlike a volcano, the magma typically does not reach the Earth's surface. That is why mountains are formed, not a volcano. Basically, it is called a dome mountains. Next, we have the fold mountains. So these are the most common type of mountain. They form when two or more tectonic plates are pushed together, causing layers of rocks on the seafloor to crumple and fold. So in this kind of situation, fold mountains are formed in a compressional stress, wherein we can see that the direction of arrow or forces is in compression. Over millions of years, these folded layers are slowly pushed up higher to form mountains. Examples of fold mountains, we have the Himalayan mountains in Asia, the Alps in Europe, and the Andes in South America. So in addition to this, fold mountains are created where two or more on Earth's tectonic plates are pushed together. These colliding compressing boundaries, rocks and debris are warped and folded into rocky outcrops, hills, mountains, and entire mountain ranges. Next, we have the volcanic mountains. A volcanic eruption occurs when magma bubbles up and eventually erupts through a crack in the Earth's crust. This causes a molten rock known as lava to flow over the land before it cools and hardens. Further eruption creates more layers of hardened lava which build up to form a mountain. Sample volcanic mountains include Mount St. Helens in North America and Mount Pinatubo in the Philippines. So as the name suggests, volcanic mountains are formed by volcanoes or volcanic activities or in the form of volcanism. Volcanic mountains are formed when molten rock, magma, deep within the earth, erupts and piles upon the surface. Magma is called lava when it breaks through the Earth's crust. So when the ash and lava cools, it builds a cone of rock and forms volcanic mountains. That ends our discussion for today. See ya next time. God bless.